There's one tissue in your body that has no blood supply of its own. No arteries running through it. No direct line for oxygen or nutrients to arrive the way they do almost everywhere else. It survives entirely on diffusion and on its own internal recycling system. That tissue is cartilage, and the cells inside it are some of the longest living, slowest dividing cells you have. So what happens to that tissue, and to the cells inside it, when the body's main cleanup process, autophagy, gets triggered repeatedly over 30 days? The answer involves a mechanism most people have never heard connected to their joints at all. Cartilage is unlike almost every other tissue in the human body. While muscle, skin, and most organs are fed directly by a dense network of blood vessels, cartilage has none. It is classified as avascular, meaning it has no internal blood supply whatsoever. Oxygen and nutrients have to travel by diffusion, moving slowly through the surrounding synovial fluid and into the tissue itself. This lack of vascularization is not a flaw. It is structural. Cartilage needs to withstand repeated mechanical load, compression, and shear forces every time a joint moves, and a dense network of blood vessels would not survive that kind of pressure. But this design comes with a trade-off. Without a direct blood supply, cartilage cannot rely on the same rapid repair and immune responses that other tissues use after damage. Its maintenance depends almost entirely on the activity of the few cells that live inside it. That dependency is what makes autophagy particularly relevant here. In tissues with abundant blood flow, damaged components can sometimes be cleared or replaced through processes supported by circulating immune cells. In cartilage, the internal recycling systems of its own resident cells carry a disproportionate share of that workload. Understanding what happens to that recycling system under different physiological conditions is the foundation for everything that follows in this video. Inside cartilage, there is essentially one type of cell doing all the work: the chondrocyte. Unlike skin or muscle, which contain multiple cell types working together, cartilage relies almost entirely on chondrocytes to build, maintain, and repair the tissue around them. These cells produce and continuously renew the protein scaffold that gives cartilage its structure, regulating its composition throughout life. Chondrocytes are notable for how slowly they divide. In mature cartilage, chondrocyte turnover is remarkably low, and the cells that are present can remain in the tissue for extended periods. This longevity means that each chondrocyte has to manage internal damage accumulation over a very long lifespan, without the option of simply being replaced as quickly as cells in faster renewing tissues. This is precisely why autophagy matters so much at the chondrocyte level. Research has linked autophagic activity in chondrocytes to the maintenance of cartilage homeostasis, with studies showing that disruption of this process is associated with cartilage degeneration. Because these cells cannot rely on rapid replacement, their internal quality control systems, including autophagy, carry exceptional weight in determining whether the tissue stays functional or begins to deteriorate. When a person stops eating, the body does not respond to all tissues identically. Many of the early signals associated with fasting, declining insulin levels, activation of the energy-sensing enzyme AMPK, and a drop in the growth-promoting mTOR pathway, circulate throughout the body and reach virtually every cell, including chondrocytes embedded deep inside joint cartilage. In tissues with strong blood supply, these signals can arrive and produce metabolic shifts relatively fast. In cartilage, because nutrients and signaling molecules travel by diffusion through synovial fluid rather than through direct circulation, the same systemic signals likely reach chondrocytes on a delayed timeline compared to more vascularized tissues. Some entry points into the joint are limited, and the leading edge of cartilage and the synovium represent a less studied biological frontier for these processes. This delay does not mean nothing happens early on. Autophagy activity has been described as a major regulator of chondrocyte survival and cartilage matrix homeostasis, and the same upstream cellular signals that trigger autophagy elsewhere in the body are present in joint tissue as well. What differs is not whether the mechanism exists in cartilage, but how quickly and to what degree it responds compared to tissues with direct blood flow, a distinction that becomes more relevant as the fasting period extends beyond the first few hours. As the body ages, the relationship between cartilage and autophagy begins to shift in a measurable way. Research comparing chondrocytes from younger and older cartilage has repeatedly found that markers of autophagic activity, proteins such as ULK1, Beclin-1, and LC3, appear at noticeably lower levels in older or osteoarthritic tissue. This pattern has been documented by Karamas and colleagues, whose work on human and murine cartilage showed that autophagy capacity in chondrocytes declines progressively with age, well before any visible degeneration appears on an X-ray or MRI. The cells are, in a sense, losing their cleanup machinery years before the joint itself shows outward signs of wear. This decline does not happen randomly. One of the central regulators involved is the mTOR pathway, the same nutrient-sensing system that governs autophagy throughout the rest of the body. In chondrocytes specifically, when mTOR activity rises, it suppresses the formation of the protein complexes responsible for assembling autophagosomes, effectively closing the cell's recycling machinery. Counterbalancing mTOR is AMPK, an energy-sensing enzyme that activates autophagy when cellular energy is low. Multiple studies have identified mTOR as a primary inhibitor and AMPK as a primary activator of chondrocyte autophagy, and the balance between these two pathways appears to shift unfavorably as tissue ages, tilting toward suppression rather than activation. The consequence of that shift is not abstract. When autophagy declines, damaged mitochondria, misfolded proteins, and oxidized molecules that would normally be broken down and recycled start to accumulate inside the chondrocyte instead. Because cartilage cannot call in new cells to replace the ones that become overwhelmed, this buildup tends to stay localized and progressive, cell by cell, for as long as the tissue survives. Several research groups have described this accumulation as a contributing factor in age-related cartilage degeneration, distinguishing it from injury-related damage, which tends to follow a faster and more localized timeline. Osteoarthritis has traditionally been described as a simple consequence of mechanical wear, the kind of damage that accumulates after decades of joints absorbing impact and load. But the age-related decline in chondrocyte autophagy described earlier raises a sharper question. If the cleanup system is already weakening with age, is osteoarthritis still just mechanical wear? Or is it partly a failure of cellular maintenance that happens to show up most often in older joints? Research over the past 2 decades has pushed toward the second interpretation, treating osteoarthritis less as a disease that simply accumulates on top of aging cartilage, and more as a condition that may share its underlying cellular cause. This finding mattered because it reframed part of osteoarthritis as something more than passive wear. If autophagy is actively suppressed in diseased cartilage, then the loss of structural integrity is not purely mechanical. It is also the downstream result of a cellular maintenance system failing to keep pace with damage. Supporting this idea, work using animal models has shown that when autophagy is experimentally enhanced in chondrocytes, markers of cartilage degeneration tend to decrease, while models in which autophagy genes are knocked out tend to show accelerated degeneration. These are associative and interventional findings, primarily from animal and cell culture models, and researchers have been careful to note that the field is still working out exactly how directly these mechanisms translate to the full complexity of human joint disease. What has become clearer is the specific molecular chain connecting reduced autophagy to tissue breakdown. Studies have shown that low autophagy activity in chondrocytes correlates with higher levels of enzymes called matrix metalloproteinases, which break down the collagen and proteoglycans that give cartilage its structural integrity. In tissue with healthy autophagic turnover, this breakdown appears to be kept in better balance by ongoing repair. When autophagy falls, that balance tips toward degradation, a relationship researchers in this field have described repeatedly across independent experimental models. Cartilage does not function in isolation. It is bathed in synovial fluid, the viscous liquid that fills the joint capsule and serves two purposes at once: lubricating the surfaces so they can glide against each other with minimal friction, and acting as the delivery channel for the nutrients and oxygen that cartilage cannot receive through blood vessels. This fluid is produced by cells in the synovial membrane, the thin tissue lining the joint capsule, and its composition is closely tied to the overall health of the joint environment. The synovial membrane itself contains cells that rely on autophagy for their own maintenance, and research on joint disease has increasingly looked at the synovium alongside cartilage rather than treating it as a separate compartment. In osteoarthritic joints, the synovial membrane frequently shows signs of low-grade inflammation, and inflamed synovial tissue tends to release inflammatory molecules directly into the synovial fluid that bathes the cartilage. Because chondrocytes depend on that same fluid for their nutrient supply, changes in its composition do not stay contained to the membrane. They reach the cartilage as well, creating a feedback loop between the two tissues. This is where autophagy's role becomes especially layered. Healthy autophagic activity in synovial cells appears to help regulate how much inflammatory signaling gets released into the joint space, while autophagy in chondrocytes determines how well those cells can withstand whatever inflammatory exposure does occur. When both systems are functioning, the joint environment tends to stay in a more stable, lower inflammation state. When autophagy declines in either tissue, researchers have observed that the synovial fluid composition shifts in ways that favor a more inflammatory, less protective joint environment overall. A relationship documented primarily in laboratory and animal model research rather than direct human trials. Inflammation inside a joint is not a single uniform event. It involves immune cells, signaling proteins called cytokines, and a cascade of molecular responses that can either resolve quickly or persist for years, depending on the underlying conditions. One of the most studied cytokines in joint research is interleukin-1 beta, or IL-1V, a molecule strongly associated with both acute joint injury and chronic osteoarthritis. Laboratory studies have shown that IL-1V directly suppresses autophagy in chondrocytes, lowering the rate at which these cells can clear damaged internal components at exactly the moment when that clearance matters most. This creates a particularly difficult cycle. Inflammation increases IL-1V levels in the joint. IL-1V suppresses chondrocyte autophagy, and reduced autophagy allows damaged cellular components and dysfunctional mitochondria to accumulate. That accumulation, in several experimental models, has been linked to further activation of inflammatory pathways inside the cell, which can in turn sustain or even amplify the original inflammatory signal. Researchers studying this loop have noted that it offers a partial explanation for why joint inflammation, once established, can become self-perpetuating rather than resolving on its own. Though work in this specific area has been concentrated in cell culture and rodent models, with human confirmation still developing, autophagy's relationship to inflammation is not limited to chondrocytes responding passively to outside signals. Several studies have also found that autophagy itself can influence how much inflammatory material gets released from a cell in the first place, partly by regulating the breakdown of damaged inflammasome components before they can trigger a broader immune cascade. This dual role, being both affected by inflammation and capable of regulating it, is part of why autophagy has drawn so much research attention in joint disease specifically, rather than being treated as a generic cellular housekeeping process with no particular relevance to inflammatory conditions. One of the most direct demonstrations of autophagy's role in joint health came from a study led by Beatrice Carames and colleagues, published in 2011 in the journal Annals of the Rheumatic Diseases. The research team induced osteoarthritis in 2-month-old mice through surgical destabilization of the knee joint, then treated half the group with rapamycin, a compound known to inhibit mTOR and activate autophagy, while the other half received a vehicle control with no active treatment. After 10 weeks, the mice treated with rapamycin showed measurably less cartilage degradation and lower histological scores of joint damage compared to the untreated group, alongside clear evidence of increased autophagy markers in their cartilage tissue. This finding mattered because it moved the relationship between autophagy and joint health from correlation to something closer to causation, at least within the constraints of an animal model. It was not simply that healthier cartilage happened to show more autophagy activity. Deliberately increasing autophagy activity through pharmacological means produced a measurable protective effect on the joint. A separate study published in 2014 in the same journal, led by Zhang and colleagues, took this further by genetically deleting mTOR, specifically in cartilage tissue in mice, which by itself increased autophagy and reduced the severity of experimental osteoarthritis, reinforcing that the mTOR autophagy axis was a meaningful driver rather than a side effect of some other process. Human research in this specific area remains more limited than the animal work, largely because directly manipulating autophagy in living human joint tissue raises far more ethical and technical obstacles than working with mouse models. What human studies have consistently shown, drawing on cartilage samples obtained during joint replacement surgeries, is the same pattern observed in mice. Chondrocytes from osteoarthritic and aged human cartilage display lower levels of autophagy markers compared to younger, healthier tissue. The mouse studies established a plausible causal mechanism. The human tissue studies established that the same biological signature appears in actual patients, even though establishing direct causation in humans. The way it was established in mice remains an open scientific challenge. If you've made it this far, you now understand something about your joints that most people never learn. That the cartilage holding your knees, hips, and hands together depends on a cellular recycling system most of us have never heard of until today. Let me know in the comments which part surprised you the most. The fact that cartilage has no blood supply, or the connection between this cleanup process and joint inflammation. There's still more ahead, including what changes after 30 consecutive days of triggering this mechanism, so stick around. Translating laboratory findings into a specific 30-day window requires some care because most of the controlled research on autophagy and cartilage comes from continuous pharmacological activation in mice rather than from repeated daily fasting-induced autophagy in humans over a month-long period. That distinction matters, and it's worth being explicit about it before describing what the existing science does suggest. Fasting-induced autophagy and rapamycin-induced autophagy activate overlapping but not identical pathways, both converging on mTOR inhibition, but operating through different upstream triggers and likely different magnitudes and durations of effect. With that caveat in place, the available evidence points toward a few plausible structural changes if autophagy were meaningfully and repeatedly activated in joint tissue over a month. Based on the mechanisms described in the rapamycin studies, sustained autophagy activation would be expected to support continued clearance of damaged mitochondria and misfolded proteins inside chondrocytes, potentially slowing the kind of intracellular debris accumulation associated with cartilage aging. The matrix metalloprotein's activity linked to extracellular matrix breakdown might also be expected to shift, given the documented relationship between higher autophagy and lower expression of these degradative enzymes in experimental models. What current science cannot yet specify is the precise dose-response relationship for humans. How many days of activation are needed before measurable structural changes in cartilage would appear? How much daily fasting-induced autophagy compares in magnitude to the pharmacological activation used in the mouse studies? Or whether 30 days represents a meaningful threshold versus a much longer or shorter timeline. Cartilage's slow turnover, the very feature that makes its cells vulnerable to long-term damage accumulation, likely also means that any structural remodeling in response to increased autophagy would unfold gradually rather than producing rapid, dramatic shifts within a single month. That gap between what the mechanism predicts and what's actually been measured in a 30-day human timeframe points to something broader about where this entire field of research still stands. For all the progress made in mapping autophagy's role in cartilage, several major questions remain unresolved. The relationship between autophagy and osteoarthritis has been described predominantly through animal models and human tissue samples taken at a single point in time, usually during joint replacement surgery. What's largely missing is longitudinal human data, studies that track autophagy markers and cartilage condition in the same individuals over months or years to establish how changes in one actually precede or predict changes in the other, rather than simply appearing together in a snapshot. There's also the unresolved question of dosage and timing specific to fasting as opposed to pharmacological intervention. Nearly all of the strongest causal evidence for autophagy's protective effect on cartilage comes from rapamycin administered directly and continuously over many weeks, not from the kind of intermittent, nutrient-driven autophagy activation associated with periodic fasting. Researchers in this field have generally been cautious about extrapolating from one trigger to the other, since the intensity, duration, and cellular targeting of autophagy can differ substantially depending on what's activating it. Finally, the relationship between autophagy and joint aging appears to be more complicated than a simple more is better model. Some research has suggested that excessive or poorly regulated autophagy under certain conditions can itself become associated with chondrocyte stress rather than protection, which means the goal in ongoing research is less about maximizing autophagy indiscriminately and more about understanding the specific conditions under which it supports cartilage health versus when it might tip into a less favorable balance. That nuance, more than any single finding covered in this video, represents where the science currently stands. A mechanism with real, demonstrated relevance to joint health, studied carefully enough to be taken seriously, but not yet mapped completely enough to answer every question a curious mind might have about their own knees. If this video helped you understand something new about how your joints actually work at a cellular level, that's exactly why I make these. If you found it valuable, hit like, subscribe for more science-based deep dives like this one, and share it with anyone who'd find this as fascinating as you just did.